Okay, let's get started. So we have 47 students today, and looks like just about one for every seat. So that's great. Welcome to CS 206 Evolutionary Robotics. This is our first class. We're going to spend a fair bit today just going over logistics and housekeeping, what you can expect from me, what you can expect from the teaching assistant, and what we can expect from you, and hopefully if we have time towards the end of today, we'll finally get into some of the lecture material. Okay, so let's just start with the various tools that we're going to use to support this course. Your main go-to site for CS 206 is Blackboard. On Blackboard, you will find, if you click on the syllabus or the course material, you'll find basically a stub here that points to a Google Drive. And in this Google Drive, I will put all of the material you need for the course. Has everyone been able to access this directory, download the reading, lectures? Okay, read permissions are all okay? Okay, so everything more or less will be here on Google Drive, including the syllabus. So I wanted to just start with that today so we're all on the same page. Obviously, we're meeting here Tuesday and Thursday morning. I apologize if you're not a morning person. We start at 8:30 a.m. That's why I like to have classes at this time. Okay. My office is over in Farrell Hall on Trinity campus, and I hold my office hours directly after this class. So if you've got questions for me, we can sort of walk and talk back towards the Trinity campus. And if it's a short question, you can turn around when we finish. If it's a longer question, we can set up camp in Farrell Hall and work through your questions. The teaching assistant for this class is Owen, and Owen is right here. Thank you. Owen is going to be holding office hours in VOTI 332, which is the CS crew room. You can find Owen there Monday and Wednesdays, 4:30 to 5:30. That's still all right, Owen?
Yeah.
Okay, very good. All right, I won't read the description. You can read that on your own. I just want you to focus on the word up here, autonomous machines. So what we're going to spend 99% of the time talking about in this class is how to make machines that are both autonomous and adaptive. Robotics is very, very popular at the moment. Most of the robots that are out there at the moment are autonomous but not quite adaptive, and some of them are adaptive but not quite autonomous. The long-term goal for all of those of us working in evolutionary robotics and roboticists in general is to create machines that are both autonomous and adaptive. And we're going to spend a lot of time talking about why that is so darn difficult. Okay. You're going to be expected to carry out a major programming project. So the bulk of this work in this class, as you're going to figure out, is a lot of programming. We're going to talk about the first programming project today. It's actually assigned today, so you can start on it early. If you're not sure if this class is right for you, start on the programming project. And if you have no problems with the first programming project, you're probably going to do okay in this course. If you find that you're struggling with the first programming project, come and see me and we'll talk about whether you're ready for this course. Okay, let's talk about the reading. There's a required textbook, Bio-Inspired Artificial Intelligence. There's only one edition of this class, of this textbook, which makes things easy. I don't stock it in the library. I'm sure you can find a cheap copy online somewhere. Okay, the optional textbook for this class is How the Body Shapes the Way We Think. I will give it to Owen, and Owen, if you can put it on loan in the library for those that are interested. It's optional. You don't have to buy it. Through the miracle of modern publishing, for every book that's bought, I receive exactly $1. So if all of you buy a copy, I'll make a grand total of $47. So no financial incentive here for me to have you buy the book. But by all means, if you feel the need to do so, please do so. Okay. Towards the beginning of the class, there's going to be a lot of readings that are drawn from the required textbook and some from the optional textbook. The further we get into the class, a lot of the readings are going to be actual research papers, so this is a good chance for those of you that haven't read first source material before. You'll actually get a chance to read some original research papers. Evolutionary robotics, the field is pretty young. It only started in the early 1990s, so there aren't a lot of textbooks about the topic, so we're going to actually read some original research papers as we go. Prerequisites, junior standing and programming experience. If you feel you're lacking one or both of these, come and see me and we can talk about it. Okay, grading scheme, there's a late policy. If your material is 1 day late, 25% off. 2 days late, 50% deduction. If you find you're more than 2 days late with your material, no need to submit it. Okay, the main spine, if you like, for this class are 10 programming projects. Each one is worth 4%. And you're going to be doing these 10 programming assignments over the first 8 weeks. There are 2 weeks where we're going to double up on programming projects. And the reason we're going to do that is so that in the final 6 weeks of the semester, you'll have plenty of time to do your final project. I'll come back and talk about these 10 programming projects, but the main thing to take away from this is these programming projects are cumulative. So basically, what you're doing throughout these 10 programming projects is building up an evolutionary robotics simulator that you can run on your laptop. So if you do miss a project or you're late, you still have to complete it before you can complete the next one, right? It's like math, it's cumulative, so really make sure not to get behind with the programming assignments. Okay, we're going to have daily quizzes. So after class on Tuesdays and Thursdays, I'll put up a short quiz on Blackboard. Should take you about 5 minutes if you came to class and if you've done the reading. And it'll be due midnight tonight. So hopefully everything is still fresh in your mind. I mentioned the final project. So for the graduate students that are in this class, you're going to be taking your evolutionary robotics simulator that you've made over the first weeks and doing an original research project. For the undergraduates in this class, I have a list of projects that you can choose from, but you can also come up with a project of your own if you have an idea in mind. Graduate students that are in the class, please put up your hand. Just one. Okay, Tyler, you're our token graduate student this semester. Okay, participation, I expect you to come to class. A lot of what we're going to do in this class is interactive. I'm going to ask questions. You might do a few in-class assignments with the person sitting next to you. So come to class. I don't expect your participation to be perfect. You can miss up to 3 classes. You'll see that there's an attendance sheet that's wending its way around. If you come to class late, just make sure you sign your name on the attendance sheet before you leave. If you find that you're missing more than 3 classes, come and let me know why. Okay, any questions about the syllabus? We're all good? Okay. So in addition, in this directory, you'll also find the schedule, and this I will update as we go along. You can see, obviously, for today, we're going over logistics. We're going to talk a little bit about why one might choose to study robots. The assigned reading is linked there, and there's a link to the first assignment, which, again, I'll come back to and talk about in a little bit. I'm recording the lectures this semester. We'll see how that goes. When class finishes, I will upload the video. I'll upload the video to YouTube and put a link to the lecture video here. So if you find that you do have to miss class, you can catch up after the fact. Okay. Okay, so let's start off with a little bit of material. We'll come back and do a little bit more logistics in a moment. We're going to talk about what evolutionary robotics is, but before we talk about what it is and telling you a little bit about the history of the field, I thought I would start with a little bit of the future of the field. 3 years ago, there was an undergraduate in this class, Nick Cheney. Nick graduated from UVM and is now doing his PhD at Cornell University. His funding at Cornell is coming from NASA, and actually Nick just flew down there a couple days ago. He's spending some time at NASA Ames in Silicon Valley in California, and he's working on a tensegrity robot, which is a prototype rover that's being developed at NASA Ames. And I will let the researchers at NASA Ames tell you a little bit about the tensegrity robot.
We're investigating how to use these really novel tensile
No. Okay, well, I will narrate for them. What you're watching here is a tensegrity robot. These bars are rigid bars, and those lines that you saw that are connecting the rigid bars are springs or things that can be contracted or expanded with a motor. This is the project lead telling you a little bit about it. This is the reason why they're interested in tensegrity robots. I'll play this again. One of the major challenges that NASA faces in any of their planetary probes, aside from getting the probe there, is how to get it to land. They've tried all sorts of things, parachutes and rockets and balloons. Tensegrity structures have this amazing property where they're soft and compliant, so they can absorb a lot of shock as they move, or in this case, as they're dropped out of whatever is delivering them to the planetary surface. So in this simulation, what you see in the middle here, this sphere is supposed to represent whatever the scientific package is that is trying to be delivered to the surface. And one of the beautiful properties of tensegrity robots is they can kind of protect that scientific package inside. Here you can see a tensegrity robot moving, where the motors that connect these stiff pieces together contract or expand the string or the spring, depending on how they build it. So you'll see them switch back and forth between simulations, like you see here, and the physical robot. All of the work that we're going to be doing in this class is in simulation. We're not actually going to be building any physical robots. So the nice thing about simulation, obviously, is we can rapidly develop a prototype of this kind of technology. So tensegrities are actually a structure that's been around since the 1970s, and just in the last few years there's been an attempt to try and turn these into robots or active structures. One of the challenges in tensegrity robots and in a lot of work in robotics is the control problem. If you want this robot to approach this object in its environment, which of these springs should you contract at what time? It's a very non-intuitive thing to do. If I were to give you a simulation of this tensegrity robot and ask you to write a computer program to manually decide which spring to contract at which time, it's an exceedingly difficult thing to do. This tensegrity robot is doing a pretty good job of it. And the reason it's doing a pretty good job at it is because it's been evolved to do so. So this is actually an evolutionary robotics project going on at NASA Ames. Another challenge to controlling tensegrity robots is they don't really look like anything you see in nature, right? So we'll see a lot of legged robots in this course that look like horses or dogs or maybe humans, where we obviously have an example out in nature that we can try and copy. In the case of tensegrity robots, not so easy. This is a demonstration of collective intelligence, or trying to get a bunch of robots to do something together. We're going to spend some time in this class talking about how to actually evolve robot swarms so they can do something together that's beyond the ability of any one of them. Obviously, this would be something that would be desirable to NASA. Instead of sending one single, very expensive machine, they might send 4 or a dozen or 100 or 1,000 of these things, drop them on the surface, and if 30 or 60 or even 90% of them fail, they might still be able to recover some functionality out of the mission. Okay, so my first answer to why might you take this class is you might get to go and work for NASA on their next generation of planetary probes. Maybe that might not be in all of your futures, but this is definitely something that NASA is thinking about. Okay. Okay, you can go and watch that video at your leisure. And listen to the program leads tell you a little bit more about that project. Okay, all of the evolutionary robotics projects that you're going to see in this course have 4 main ingredients. And if 30 years from now you forget everything in this course, and your old Professor Bongard emails you or whatever exists at that time and asks you, what are the 4 basic ingredients of an evolutionary robotics experiment, I'm going to expect 30 years from now that you'll have this answer for me. All of the robots that we're going to study, regardless of whether they're simulated or physical, are existing in a task environment. Usually we've given them something to do, and they're trying to figure out how to do that. Obviously, we have the robot itself, and in a couple lectures from now, we're going to spend some time talking about what are all the building blocks that go into a robot. What needs to go in there for a robot to be different from your cell phone or a laptop or a projector? What is it that distinguishes robots from all other electronic technology? Inside the robot, it has a brain or a neural model, more commonly called an artificial neural network. We're going to spend a bit of time in this class talking about artificial neural networks, but not too much time, just enough for you to be able to implement a brain for your robot. Professor Snap is offering a class, Neural Computation, this semester. If you're really interested in artificial neural networks and you want to dig into that, if you haven't signed up for his class, you might consider doing so. Okay, so we've got the world in which the robot exists. We have the robot itself, and inside the robot we have this artificial neural network, which is controlling how the robot moves in response to what it senses. So in essence, what the ANN is doing is transforming sensory signals into actions, which is ultimately what all of our brains are tasked with doing as well. Okay. What should that artificial neural network look like? And in some cases, what should the body of the robot look like? As we just saw in the tensegrity robot, very difficult to know how to control that tensegrity robot. So in this class, what distinguishes evolutionary robotics from all other branches of robots is we use a particular algorithm called an evolutionary algorithm to optimize the artificial neural network so that the robot does what it's supposed to do. As you can probably tell from the name, we're going to steal a lot of ideas from Mother Nature, and instead of allowing the robot to learn, instead we're going to use evolution, which is at its heart a trial and error process. So here's a simulation from one of my own experiments from a few years ago. What you're watching in this simulation now, every few seconds, you're seeing the best ANN that the evolutionary algorithm has found so far. Let me just pause this for a moment. So what you're not seeing is a whole bunch of ANNs that failed, right? So evolution, most of the time when it produces a mutation or it sexually recombines genetic material, the child is as good as the parent, or in some cases the child is not as good as the parents. It's a deleterious mutation. Every once in a while, a mutation occurs that makes, in an evolutionary robotics experiment, the new robot, the child robot, slightly better than the parent robot. So what you're watching in this video, and I'll just start it over, is you're watching the best ANN in the population at that time. And as you watch this progression, what do you think it is that we've asked this robot to do? What is the task that it's supposed to be performing in its environment? Yes?
Put the block on top of it.
Absolutely. So pick up the block and put it on its back. And inside this robot, there's an ANN, which is taking sensory information, whether it's touching the object, how much strain it feels on its arms, whether its feet are in contact with the ground or not. It's taking all this sensory information, and that sensory information is being passed into the ANN, and the ANN outputs how the robot moves. The evolutionary algorithm is tinkering with this ANN, and we'll get into the details of how this works later, tinkering with it in a trial and error way until ultimately it finds this ANN, which, when we place this blue block in front of the robot, allows it to pick up the block. So this video, which you just watched, was an evolutionary algorithm, but I only showed you a few snapshots from that process. I'm going to play you the video on the right now, and we're going to speed up this evolutionary algorithm even faster. What you're going to see in the first second or so of this video is this last ANN, the one that's evolved to successfully pick up the block. At the end of this 1 second, when the robot has successfully evolved to pick up the block, we're going to change the task environment, which is going to make this ANN, which allows the robot to pick up the block, to fail. The world around the robot is going to change slightly, but we're just going to keep running the evolutionary algorithm. This trial and error process is going to continue, and it's going to try and adapt to changes in its environment. What change are we making to the task environment? Moving the block 1 millimeter further away from the robot. And again, I'm only showing you the successes, not showing you the failures. You're going to have a very long blooper reel at the end of this course, I promise you. The task is still the same, right? Grab the block, pick it up onto its back. What's happening? All right, this video can be a little mesmerizing. Let me pause it here for a moment. What's happening? We're asking the robot to do exactly the same thing. Get the block and lift it onto its back. And we just keep evolving brains for this robot that managed to do so.
We're forcing it to walk.
Forcing it to walk, absolutely. So there's nothing in here where we've asked the robot to walk. It's a side effect of the way we're evolving the robot. And you're going to see many examples of that as we go along. One of the interesting things about evolutionary robotics, and one of the challenging things about evolutionary robotics, is that our robots often act like teenagers. They do what we ask them to do, but not in the way we were expecting them to do it. Right? In this case, I kind of had an idea that they'd have to walk, or they'd have to at least get to the block somehow. Right? Okay, so we started with just reaching and lifting, and now we've got walking. What else is happening here? We're not just getting walking. What else do you see besides walking? Yes, in the back.
Constantly grabbing at air, trying.
It's constantly which?
Grabbing at air, to try and get to the block.
Yes, so why is it bothering to do this before it's even gotten to the block?
To figure out if it's at the block.
Could be, because it's trying to figure out whether the block is there. Why else might it be doing this rather than just waiting until it gets there and then...
It doesn't actually know that being at the block and doing that is what makes it go, so it just keeps on trying until it works.
That could work, right? Just keep blindly doing this and hope that you do this when you get to the block and not this. There's a third reason why it might be doing this while it's walking there.
Does it help with its momentum moving forward?
It could be. You might notice that the pincers kind of move in synchrony with the legs. That could be, actually, I haven't heard that one before. That could be a possibility. We could test that.
Could it be for balance?
Could be for balance, maybe. We swing our arms in anti-phase when you run so that you keep your balance.
It's because it evolved from the original when it closed down the
right at the beginning.
Absolutely, right? So what you're watching here are evolved brains, but those brains are the great-great-great-great-great-great-grandchild of the brain that you saw here, which did this. This is an idea that we're going to see many, many times in these experiments, and this is a term from biology, exaptation. So Mother Nature is, or evolution is ultimately lazy, so she will tend to exploit previous adaptations if they're there, rather than creating something from scratch. So rather than our evolutionary algorithm throwing away this behavior, which works, now it doesn't work when the block is a little further away, but with a few little tweaks, it still works. So you can see Mother Nature here in the form of our evolutionary algorithm exapting a previous function and adapting it for the new situation. So the bones in your inner ears were bones that were originally used in our reptilian ancestors in their jaws for crushing. So mammalian hearing did not evolve from scratch. It was exapted from a structure in our reptilian ancestors. One of the cool things about evolutionary algorithms is, again, it's still a computer program, but you'll see this computer program recapitulating or using a lot of techniques that we see in nature as well. So one of the interesting things about evolutionary algorithms, we can use them for an engineering purpose to design machines, but we can also use them to go back and study biology and try and understand better where we came from and how we evolved. What else do you see going on here? We see the evolution of walking. We see exaptation. What else is happening here that's perhaps a little bit surprising, given the description I gave you before I ran the video? Not quite what we had in mind, right? Is it always walking in the same way? Definitely not, right? So the kind of the opposite of exaptation here is variation. So I asked for a particular behavior, get to the object, grasp it, and lift it onto your back. But you can see here that this evolutionary algorithm comes up with lots and lots of different solutions, and some of them might be what we had in mind, and some of them definitely not. So this is another powerful advantage of evolutionary algorithms, is often they don't give us back one solution to our problem. They don't give us just one robot or one behavior. They give us a range of different behaviors, and perhaps after the fact we select which of these behaviors we're interested in. Okay, 4 basic ingredients in an evolutionary robotics experiment. We can see all 4 of them at work here. As I mentioned, we're going to see a lot of different evolutionary robotics projects in this course. One good way to sort of solidify your understanding of the material in this course is every time I introduce a new robot in a new project, mentally check and see if you can identify in that project what's the environment, what's the task, what have we asked it to do. Yes?
How much of a black box do these things get? Like after a day, can you just not go back in there because it's too complicated?
That's a very good question. So how black box is it? If we were to break open this robot and look at the artificial neural network, how well could we understand it? Most of the time, not very well at all. This is one of the disadvantages of evolutionary robotics. We can often evolve something that works, but maybe not quite understand how or why it works. But we'll come back to the issue of black box in a little bit. Okay, so for every new project, see if you can identify the environment. What is the task the robot has been asked to do? Do you understand basically what the robot is? What is its body made up of? What are the sensors? What are the motors? Do you understand the artificial neural network? Do you understand the details of the brain that's driving the robot? And do you understand the basics of the evolutionary algorithm that produced this optimized ANN? I don't expect you to memorize all the details of every project we talk about, but you should be able to identify basically these 4 pieces in most of the projects we talk about. Okay. Any other questions before we continue? Okay, a little bit about who I am. I did my undergraduate in computer science, like most of you, at McMaster in Canada. After I finished my undergraduate, I went and worked for a year as a software engineer in Calgary and realized that industry was not for me. Came back to academia. I carried out a master's in Brighton, England. This is a particular master's program that at that time was the only graduate program in the world for evolutionary robotics. As I mentioned, this is a very young field. It only started in the early 1990s. This particular master's program, they invited biology students and computer science students. The biology students had to take programming classes, and us computer science students had to do bench work, dissections, and literally get our hands dirty so you could appreciate the other side of the coin. I finished my master's in England and went on to go do a PhD at the University of Zurich with Rolf Pfeiffer, who's the co-author on the book we wrote, focusing now particularly on evolutionary robotics. When I finished in Zurich, I went to go do a postdoc after my doctorate for 3 years at Cornell, working with Hod Lipson. We're going to see a lot of evolutionary robotics projects that have come out of Hod's lab at Cornell. We worked on a project there for NASA, not the tensegrity robot that you saw, but another project, and I'll talk about that towards the end of the class. After 2006, I came here, became a professor in evolutionary robotics. So if we had more time, I would go around the room and ask you a little bit about yourself. I used to have 12 students in this class. We now have 47. Hopefully I'll get to know some of you as we go along. Okay. Let's talk a little bit about expectations. So what I expect from you, as you've already seen, I'm going to ask questions from time to time. Best way to do well in this class is participate. Ask questions, respond to questions, so on. Common sense, regular but not necessarily perfect attendance. I already mentioned that. Hard work. For those of you that are not expert programmers, you're going to be putting in a fair number of hours on these programming projects. Budget your time accordingly. I mentioned memorization of key concepts here. I used to have a midterm and a final exam in this class. I don't anymore. I found that these regular quizzes throughout the course is kind of a better way to do things. So if you were hoping for a midterm and a final exam, you're not going to find it in this class. Instead, you're going to find a lot of practical work on your programming assignments. And I'm going to expect from you in your final project a lot of creativity and self-learning. So I mentioned before these projects, the first 3 of them are in Python and the final 7 are in C. How many of you have programmed in Python before? Good, okay. How many of you have programmed in C before? Okay, most of you, some of you not. Again, it's going to be expected that you teach yourself or you get online and find a tutorial and brush up on your Python or C if you feel that you need it. Positive attitude probably goes without saying. Okay, what you can not expect from me, and by me I mean myself and Owen the TA, don't come to us with your code and say my code's crashing, can you find my bugs for me? Neither Owen nor I can probably find them. It's going to be up to you to do so. As I mentioned, this is an upper year course. You're expected to figure out how to install Python, how to install the physics engine we'll be using, and so on. Okay. Okay, what you can expect from me and from Owen is we can help you with specific programming questions that are conceptual questions. So if you're new to C, we're going to be doing a little bit of allocation and deallocation of memory. This might be a new concept to some of you. If you haven't seen it before, consult online resources, see if you can figure it out. If you're still confused, come and see us and we can try and help you through that conceptual hurdle. I'm happy to help you with any of the conceptual issues that we talk about in class. Clarification about the assignments and project. You can see I struck out midterm, no more midterms. What you can expect from me and from this course in general is there's going to be an emphasis on concepts rather than specific tools, right? Evolutionary robotics in particular and computer science in general, the tools come and go, right? Python is popular at the moment. Deep belief networks are popular at the moment, which we'll talk about 5 years from now. Who knows? We're going to try and focus on the concepts which are probably going to endure, and the particular tools that we use, not so important. So again, when we talk about different projects and different robots, I don't expect you to remember all of the nitty-gritty details, but to remember why I introduced that particular robot or that project. All of the projects that I'll introduce, I'm usually using them to highlight particular concepts. So if you're going to remember something, remember the concepts and the tools, make sure you can use them, but you don't need to memorize all the nitty-gritty details. Okay, that's expectations. Let's talk now a little bit about these 10 programming projects. I'm going to just touch on the surface here with them. There's 10 of them, as I mentioned. They're cumulative. And at the end of these 10 programming projects, you're going to have 2 executables that are running in parallel. You're going to have a Python program that's running continuously and a C application that's running continuously, and they're going to talk to one another. The Python program is going to be responsible for running the evolutionary algorithm. It's the one that's going to maintain all of the genetic material that describes your robot. Your C program is going to run the physics engine. So you've already seen a few videos now. All of the robots that you see in simulation are being simulated inside a physics engine, and we'll talk more about physics engines in a couple classes from now. So your Python program is going to maintain your evolutionary algorithm. It's going to take a blueprint for the robot. It's going to store it into a file on your computer. And the C program is then going to read in that blueprint and create the robot according to that blueprint. Once that robot is created, the robot is turned on, the robot does its thing, it reacts to its sensory stimulation in whatever way it's supposed to, the robot moves around, and your code is watching that robot as it moves around and is measuring something about the behavior of the robot. So in the robot that was grasping the blue cube, we talked verbally about what the robot is supposed to do, right? Grasp the robot and lift it onto its back. We need, for our physics engine, to return a single number for us, which is the fitness. How well did that robot do? What do you think the equation was, or what was the thing that we were actually measuring to determine how well the robot did at finding and grasping and lifting the object? If I told you that's what we wanted the robot to do, and you had to write something into your physics engine here and measure something about how well the robot did, what would you actually measure?
Maybe a final distance between the block and the robot's back.
Absolutely. So you could see that sometimes it lifted it and the object fell off the robot's back, so we weren't quite capturing it at the last time step. But what we should have done actually is measure right at the last time step, right at the end of evaluating one of those single ANNs, how close was that blue object to the center of the top of the robot's back, right? That distance is the thing we probably wanted to capture. And that number we would have sent back to the Python program. Okay. That's basically what you're going to do. You're going to be setting that up in the first 8 weeks of the class. And once you have this loop closed, you can evolve things over here, send blueprints over there, change what you measure over there, get a single number back, which indicates how good that robot is. And because it's an evolutionary algorithm, as you can imagine, the evolutionary algorithm keeps things that have high numbers. Or if we're measuring distance, we want to minimize the distance, then it's keeping things that have low numbers or things that do well. Everything that does not so well, the computer deletes, and the things that remain, it makes random modified copies of it. It mutates those blueprints, sends the mutated blueprint, sees how well that new robot does, and around we go. Okay, so if you get lost in the rough as you're going along with in the 10 programming projects, come back to this slide. This is the overall architecture that we're heading for. Okay. In the first 3 assignments, as I mentioned, you're going to be building up your Python program. We're not going to be doing any physics engine. You're going to be building a very simple evolutionary algorithm in here, and then in assignments 4 through 10, you're gradually going to be building up your physics engine. Here's a list of all of these assignments. Create an optimizer or create an evolutionary algorithm. In week 2, I'm going to bunch up assignments 2 and 3. That's where we're going to focus on building these neural networks. Assignment 4 is when we're going to start in on the physics engine. Most students I found spend most of their time on assignment 4, mostly because of installation issues, getting comfortable with C, getting a C compiler set up, getting familiar with the physics engine. So definitely allocate plenty of time for assignment 4. In assignment 5 through 10, at the end of assignment 4, you're going to have an empty physics engine, and you're going to place some objects in there. So just some shapes, which are the things that make up your robot. In assignment 5, you're going to add joints, which are the things that connect the objects together. After that, you're going to be adding motors to the joints, so things that apply force and cause the objects to rotate or move relative to one another. In assignment 7, you're going to be adding sensors to the robot so the robot can sense its virtual environment. We're going to do assignments 6 and 7 in week 5. Then in assignment 8, we're finally going to put the brain into our robot that we developed in assignments 2 and 3. And then finally, we're going to evolve the neural network, just the brain of the robot in the physics engine. And then finally, in assignment 10, we're going to evolve behavior. We're going to ask the robot to do something and evolve and check that it does what we asked it to do. Okay. Any questions about the programming projects? Yes?
So I noticed for everything you said C, but one slide had C++. I was wondering.
Yes, you can get, there's going to be a little bit of C++. I'm going to try and hide as much of it as possible. Most of what you're going to be doing in C. If you're new to C, I would suggest doing a tutorial on that. Actually, I think I missed it here. I put in a URL here to Codecademy. Has anybody used Codecademy before? I think of all the online tutorials, this is the one that I've heard the most good things about it. It's interactive. So go brush up on your C skills. If you have time, you can brush up or learn C++. But I think most of what we're going to be doing is in C. Any other questions about the 10 projects? Okay, so that's the conceptual side of the 10 projects. So I want to just switch gears now and talk a little bit about the logistics of these assignments. So how do you actually find them and submit them? So I'm going to go back to Blackboard here. There's a little bit of a roundabout process for doing and submitting your solutions to the programming project, and that's because I'm running this class as a hybrid class. So I have all of you here. I also have people out on the web who are taking part of this course online. So they are also going to be submitting solutions to their project. That's why we're going to do this in a little bit of a roundabout way. So bear with me. So I'm going to write this out as just a long chain. So for the assignment, obviously, you're going to start in Blackboard here. In Blackboard, if you go to Course Materials, you will see now assignment 1 is there. It will go live at midnight. Monday night. So that's when the assignments are due. Your assignment is due Monday night, and the new one goes live Monday night. So we've got assignment 1 here. The instructions are here, which will take us to our Google Drive. Here are all the instructions for what you'll be doing in assignment 1. I'll come back to this in a moment. You'll notice a number of links here. If you click on any one of these links, this will take you to Reddit. Everybody here familiar with Reddit? Most people, yes. Okay, if you haven't, very simple. Let me just go to our subreddit here. You'll notice that there's a whole bunch of links here. You just post your link and then people can upvote and downvote your link. So you're going to be posting your submissions actually in Reddit. Okay. So we're still in Reddit here. This contains the actual instructions for carrying out the assignment. In the first assignment, you're going to be doing the .bot project here. Click to next steps. This is all described in the instructions here. It's a video tutorial. Set of tasks. There's some pseudocode there for you if you need it. At the end of every assignment, your submission is going to be not code, not an essay, but screenshots. So I've designed these screenshots so that it's easy for myself or the TA to look at the screenshots and know whether you've implemented that assignment correctly or not. Okay, so you go to Blackboard to find out about the assignment. Go to Drive, which has the set of instructions. In Drive, there'll be links to the actual instructions in Reddit. Once you've finished the assignment, you should have these 3 images. And let me start here. You're then going to upload your images somewhere on the web. There's a link there to Imager. It doesn't really matter to us. Wherever you want to just drag and drop your images somewhere on the web, that's fine with us. Once you've dropped your images there, you will come back to the instructions. And let's see here. Should be here somewhere. And at the end, we'll go through, I think the instructions are actually back in Drive. Let's go back to Drive here. Right. Okay. So once you have your 3 images and you have the URLs for those images, you go to our subreddit here and you post a submission. And in that submission, you have links to your images. Have I lost you yet? Are you all good? Okay, so you're posting your submission to Reddit. In your submission, there are all the URLs that point to your images. Final step is you come all the way back to Blackboard. And in order to get your submission graded, no, that's not what I meant to do. Once you've created your images and to get it graded, you just write a submission, and in that submission, you just include the URL that points to your Reddit submission. So then we can grade it. Okay. Blackboard to find out about the assignment, find the instructions for that particular assignment. Those instructions will take you to Reddit. Reddit will walk you through step by step how to implement that assignment. When you get to the end of that assignment, you'll have a number of screenshots. Take those screenshots and upload them somewhere on the web. Come back to Reddit, post a submission on Reddit that points to those images, go back to Blackboard, and post a link that points to your Reddit submission. Again, I apologize for the roundabout nature of that, but in order to do that, that allows your fellow students out there on the web who are participating through Reddit to also submit their submissions, but obviously they're not being graded. Okay, any questions about that? Best thing is probably just to read through the assignment and all the step-by-steps are there. Okay. I want to just come back to the assignment for a moment. As I mentioned, each week your assignment for that week is due Monday at midnight. So next Monday at midnight, Monday the 25th, you'll be submitting your solutions to assignment 1. Assignment 2 and 3 will go live next Monday. And next Tuesday morning in class next week, I will talk you through assignments 2 and 3. So I'll set aside time at the beginning of class on Tuesday to talk about the assignment. I'll also set a few minutes aside at the beginning of class on Thursday to talk about the assignment. So get started on the assignment early. If you get stuck, Thursday is your time to ask any quick questions in class. Otherwise, come and find us for office hours. Okay, so in assignment 1, you're going to be implementing the simplest possible evolutionary algorithm. I'm not sure if you would even really consider this an evolutionary algorithm. It's called a hill climber. And I'll tell you why it's called a hill climber in a moment, but let me start by describing how the hill climber works. You're going to start by creating a parent blueprint, and in our case, this parent blueprint is going to be nothing more than a string of floating point numbers. Ultimately, this string of floating point numbers is going to become a blueprint that describes a robot, but obviously we don't have a robot, we don't have neural networks yet. All we have is a vector of floating point numbers. You're going to develop a fitness function, which is something that measures the fitness of that vector. Any evolutionary algorithm is measuring all of these things and determining which things are better than which else. The things that are not so good, the evolutionary algorithm throws away. The things that have slightly higher fitness, the evolutionary algorithm keeps, makes copies of them, introduces a slight mutation, measures the fitness of those, and around you go. So the simplest version is we're not going to have a population of things. We're just going to have a single thing, the parent, just one. We're going to take this vector, and your fitness function is going to be very simple. It's just going to sum all of the numbers in that vector. That's it. So we're reducing our vector down to a single number. Let's say the fitness of this parent, the sum of all those floating point numbers, is 1.7. We take this parent, we make a copy of it, and when we make a copy of it, we introduce a slight random mistake, which is an abstraction of biological mutation. And now we compute the fitness of this new child genome, or this vector, and we assign it a number. Let's say in this cartoon example here, the sum of this child is 1.4. It's slightly lower or worse than the fitness of the parent. Given what I've just said, what do you think we do with the child? Toss it. That's right. It's not as good as the parent. Delete the child. We're back to just one vector of floating point numbers. Do it again. This is evolution, right? Red in tooth and claw. It's a little bit harsh, but there you go.
Because we can go back from mistakes.
Sorry?
Well, I mean, in evolution, like, if you make a mistake genetically, it's just around.
Ah, yes, that's a very good question, right? There can be a deleterious mutation in nature and you manage to survive. This is clearly not an accurate representation of what actually happens in nature. We're going to start with the simplest possible thing. And one of the themes you're going to see throughout this course is we're going to look at more and more sophisticated evolutionary algorithms that keep adding more and more details and more complexity to this algorithm until we start to approach something that looks like what's going on in nature. But our hill climber definitely doesn't, right? Not yet. Okay, so in our example here, the child was worse than the parent, so it died off. We produce a new child, introduce a new mutation, a slight random mistake. This one gets this fitness. What do you think happens now? Toss the parent, right? Child is more fit than the parent. Again, this is evolution. It's a tough game. The child now becomes the parent, and around we go, right? Produce a child from this parent and iterate and iterate and iterate. The parent, or the child, as I mentioned, is just a vector of numbers. I've told you what the fitness function is. So when we run this hill climber and we get to the end, what do you think that vector looks like? What are the numbers you expect to see in that vector? All close to 1, assuming that 1 is the maximum, which it is here, right? So we can know that our evolutionary algorithm is working if these numbers get higher, and we would expect, if we look at this actual vector, that the numbers are all approaching 1. Right? So the other reason why you're producing these screenshots, let's see. Let me go back to the screenshots here if I can find them. There, here we go. So these screenshots, as I mentioned, make it easy for us to diagnose whether there's anything wrong in your code. They're also there to help you diagnose that everything's okay in your code. So here's a screenshot showing running one of these hill climbers. The horizontal axis here, it says generation running from 0 to 5,000. So a generation here is one iteration of a parent producing a child. I mentioned the fitness function is just summing all of the elements in the vector. I apologize, I misspoke. You're summing them and dividing by the number, or we're taking the average of the vector. So what happens over time here? Given this curve that's drawn, what can you tell me about the hill climber that produced this picture?
It got better very quickly and then leveled out.
Then it leveled out, exactly, right? This is what you should expect to see. If you run your hill climber and you plot the value of the parent at every generation, and it goes up more or less as a straight line, something's wrong, right? So the key to success in this class, as you work through the programming projects, is to use your screenshots and compare them against the ones embedded in the instructions. And if your picture is different from the one in here, something's wrong. And hopefully it should give you a clue where to go back and look for the problem. Why do you expect that the hill climber makes such rapid improvement and then flattens out? Why doesn't it grow as a straight line?
Is it because it like fixed all the easy problems first?
Sure, if I give you a random, exactly, if I give you a vector of random numbers between -1 and 1, and we're randomly making a few changes, it's pretty easy to increase the mean of that vector. If out here, I give you a vector that's all 0.99s and a few 98s, and you randomly change a number, most of the time things are going to get worse, right? It's only very rarely that you're going to make improvements to something that's already almost completely optimized. Right? So again, hopefully these screenshots help you to debug your program and to build up an intuition for what this program is doing and what you expect it to do. Okay, and the rest of these screenshots are explained in the instructions. Okay, so let's carry on. So I talked about the first 10 programming projects, which you'll finish at the end of week 8. After week 8, you are free to choose a project of your own choosing. Here's a few of them here, but better than that, let me jump to Reddit itself, and you can actually see some of the projects that were carried out last year. So here's Core 10, or the 10th and final assignment. And here are all the assignments that here are all the final projects that students did last year. Someone was interested in ballistic motion or jumping. Someone looked at classification, so distinguishing between friend and foe, evolving a biped or a two-legged robot, object manipulation we've already seen. Browse through some of these and you can get a feel for what's possible at the end of this class. As I mentioned, the undergraduates, you can pick something from this list or the list that's on the slide. If you have an idea of your own, in week 7 or 8, come and see me and we can talk briefly about whether it's something that's doable in 6 weeks. Okay. Okay, so we've got about 15 minutes left, which should be enough time just to sort of motivate why you're here. So I'm going to start with talking about why we might spend so much time thinking about robots and trying to build robots, or in our case, evolve robots. I start most of my lectures with these 4 images. If any of you have heard me lecture before, you've probably seen these 4 photographs. If you have, don't give away the answer for those that haven't. Okay, so the 2 photographs in the top show the way in which we build things indoors, or how the way we build things indoors has changed over the last 100, 120 years. The pair of images on the bottom shows the way in which we build, how the way we build things outdoors has changed. So we've changed the way we build things indoors, and we've changed the way we build things outdoors. What's the main difference between these 2 historical trajectories?
One is automated.
One is automated, and one is not, right? So Henry Ford, over 100 years ago, came up with the idea of mass production. So you have a whole bunch of workers, and they go and do one small thing or one small improvement to the machine. In Henry Ford's day, that was people. So mass production paved the way for automation, right? So now we have machines doing one small thing. And of course, we could talk about the ethics of that. And when we talk about robotics, there's a lot of ethical issues we could talk about. We're not going to talk about that in this class. If we have some time at the end, we'll talk about the ethics of robots taking our jobs. For now, let's just focus on the objective fact that it did happen. Okay. Why did it happen? Well, obviously, if we have this systematized production process, it's easy to automate it, and we can build many more things much more cost-effective. But this automation has not occurred in the way we build things out of doors. Why not?
Indoors, there's like a controlled environment. The robots don't have to adapt, but outdoors, the environment is variable, and the robots would have to adapt.
Absolutely. Absolutely, right? So here we have an uncontrolled environment. Here we have a factory which was designed to be exactly that, a controlled environment. So over 2,000 years ago, the Greek philosopher Heraclitus said, "Man never enters the same river twice." So I've given hundreds, maybe thousands of lectures about robots by now, but I've never given it to this group of people. You've never asked or responded to questions in quite the same way. So what do? I try and adapt my explanation as we go. Industrial robots are autonomous. There's no one driving them. They were programmed, but once they're programmed, they autonomously just do the same thing over and over again, but they're not adaptive. If we wanted to have robots that helped out at a construction site, maybe they're not even very complicated machines. All they do is clean up the construction site at the end of the day or move bricks to this pile and tools to that pile. But even simple things like that, they're going to have to adapt the way they do it at every new construction site. This is what's holding up robotics. So both robots and computers were basically invented at the end of the Second World War. And look at our computers today. Look at the advances in computers. Robots, maybe now in the last few years we've made some advances, but they're not that much more sophisticated than they were in the 1950s. And I'll actually show you a video from the 1950s in a few weeks, and you can compare today's state-of-the-art robots against one from the 1950s. So I usually argue the main thing that's holding up robotics is we don't know how to build adaptive machines. We know how to build autonomous machines. We've built industrial robots. We know how to build complicated machines. We've built the International Space Station. We've built the internet. We don't know how to build adaptive machines. Okay. Another reason why robotics is interesting is from a purely intellectual point of view. Clearly, if we could build adaptive machines, they would have huge economic value. There'd be a revolution. We would have autonomous cars. There's no doubt that there would be a practical use to building adaptive and autonomous machines. But what about the intellectual side of things? One of the things that originally drew me to robotics is it's an open frontier. There is no central guiding principle in robotics. If you look at most of the other branches of science and engineering, there is usually some central thing that's been worked out that guides all research in that area, right? Biology, pretty straightforward, right? Darwin came along and said there's this pretty simple process which explains a whole lot of what you see in nature. Physics, we have Newtonian quantum mechanics. And the standard model, which seems to be, at least for the moment, explaining most of the physical world. What's the guiding theory in chemistry? There's some central assumptions in chemistry that seem to guide everything. What are they?
Atomic theory.
Atomic theory, right? There are these small things called atoms, and you put them together, you get molecules, there's different types, and on and up you go. You have this thing called the periodic table, and if we discover a new element, it's pretty clear where it fits in that table. There's something that guides research in that area. In AI and robotics, who knows, right? It's still kind of an open frontier. I think there's several Nobel Prizes waiting to be won in this field. Maybe one of you will win one of them. Okay, so it's a field, one of the, I would argue, probably one of the most open branches in science. It's also one of the most interdisciplinary. So this is a computer science class. We're going to do some computer science in this class, but we're also going to spend a lot of time in lots of different branches of science and engineering, psychology, and even philosophy. You've already seen how we're going to have to learn a little bit about evolutionary biology. We're going to be evolving brains for our robots, so we better understand how these brains work. We're going to spend a little bit of time in cognitive science. So if you have a brain, how do you use it to do smart things? We're going to touch on psychology. We're going to touch on biomechanics. So as you move around your world, how do you do it in an adaptive and an energy efficient manner? We're going to spend some time building physics engines, building up a relatively physically realistic environment for your robots. So we're going to have to do a little bit of physics, not too much beyond high school physics, don't worry. We're going to do a lot of programming, obviously. We're not going to build any physical robots in this course, but we are going to have to pay attention to some aspects of engineering. We're even going to get into chemistry. We're going to see towards the end of the class, we're going to spend some time talking about soft robots, 3D printed robots, robots that are made out of exotic materials. Going to take us into chemistry. We're going to do a little bit of mathematics. And also, even we're going to shade into philosophy of mind. What does it mean to be intelligent? Could you point at a robot and say that robot is intelligent or self-aware or conscious? Can a robot have free will? That obviously will take us into philosophy. Okay, so some of the things that I think are cool about robotics. Let's sort of narrow in our motivation here. Why do we want adaptive machines? Well, obviously we want adaptive machines because we want them to do stuff for us outside, right? We're starting to see the beginnings of autonomous cars, and this is one of the first inroads, pardon the pun, for outdoor adaptive machines. Why are autonomous cars one of the first outdoor robots we're starting to see? Any ideas? Yes?
It's a semi-controlled environment.
Exactly, right? If you're on a highway, hopefully you can assume there's no pedestrians around. It's not quite true. So a highway is somewhere between a factory and everyday world, right? So it's not surprising that at least now, just this year, we're starting to see the beginnings of autonomous cars. Okay. Aside from autonomous cars, why might robots be useful out of doors? Well, as I mentioned, I gave you the two images of construction, building things out of doors. One of the great things about industrial robots is they allow us to scale up how we build things indoors. I would argue that if we want to solve a lot of our energy issues, and others have obviously argued this, we're going to have to build very large outdoor infrastructure. And that outdoor infrastructure might be wind farms, wave farms, solar farms, geothermal farms, who knows. But you'll find that in most of the systems that are out there, you find farm in the word, which means something where there's lots and lots of units deployed over a very large area. A lot of these things we can already build, and we have built them, but they're not quite cost effective, or they're just on the edge of becoming cost effective now, because they're expensive to build and deploy. And what is the major fraction of that expense? If you buy and deploy a wind farm, where does 90% of your money go?
Hiring people to build a wind farm.
Labor, right? Which is fine, but if we want to build very, very large wind or wave or solar farms, we're going to have to automate it somehow. Now, who knows what's going to happen in the future, but that seems to be the way things are going. Okay, so that's why robots is interesting, why we might want to build adaptive machines to help us build things outdoors. Let's narrow in now in the last few minutes that we have on why study evolutionary robotics. Evolutionary robotics is a very, very small subset of the large field, the much larger field of robotics. Depending on how you count, there's maybe 20 to 50 of us that actually work in evolutionary robotics, very small field. Why is it an advantage? Well, there's several reasons. One of them is that creating a controller or creating a brain for our robots is non-intuitive. And I've already shown you one example of this with the tensegrity robot. Here's another example. Okay, here we go. What you're seeing on the right here, this is known as a Stewart platform. And it's an interesting mechanical construction, Stewart platform. You can see that there are two platforms, and they're attached together with 6 linear actuators or pistons, which can extend or contract. And as they extend or contract, you can see that the plates move relative to one another. If you look down here, this is the nonaped robot, and I'll show you a video of this robot in a moment. Nonaped because it has 1, 2, 3, 4, 5, 6, 7, 8, 9 appendages here. And the nonaped robot is made up of 2 Stewart platforms attached end to end. Here's one Stewart platform, here's a second one, which means we have a total of 12 of these pistons. So I've listed them as M1, M4. Let's imagine there's 12 rows in this matrix here, M for motor. So you can control the 12 motors that extend or compress each of these 12 pistons. And at any point in time, T1, T2, and so on into the future, you can send a +1 or a -1 to that piston. And I want you to get this robot to walk. All right. Let's build this matrix. How would you do it? Which pistons are you going to pull and push at what time? What do you think would happen if we sent -1 to all 12 of these pistons at once? What is this robot going to do? It's going to contract, right? Like an accordion. It'll just pull itself in. What happens if we send +1 to all 12 of these pistons? It'll expand, right? So it'll be like an accordion, out, in, and won't go anywhere. So that's not going to work. Any ideas? Turns out it's not an easy thing to do. So instead of us creating this controller by hand, let's let evolution do it. So this is a project that I worked on when I was still at Cornell. Here's the nonaped in action. We put it in this huge wooden cage here so it wouldn't hurt anyone. It was a pretty strong robot. Okay, here it goes. So what you're watching here is evolution trying out some matrices on this robot, right? A matrix is just +1s and -1s that control whether the robot extends or contracts. And you can see the robot basically stretching. Not quite, huh? Little progress. You think that's the fastest this thing can go? Probably not. Turns out it can move sideways. Not bad. So these are a few matrices that the PhD student working on this project actually wrote by hand. And if you go and Google the nonaped, you can go and watch the evolved gaits or ways of moving for this robot, which go much faster than what the PhD student was able to come up with. Okay, I think we're out of time, so we'll talk about the other advantages of evolutionary robotics on Thursday. When I get back to my office, I'll post the quiz on Blackboard, so make sure to finish the quiz tonight by midnight. Get started on assignment 1, which is due next Monday night, and we'll see you on Thursday. Stay warm.